So welcome back from your lunch break or watering your plants or whatever you did for the past half hour. It's now time to resume the Glenn Symposium for 2021. Gosh, it's almost over. It's amazing. This and one more session, I think, and then we'll be done for this year. And we will start planning next year immediately. Now we're going to present the second of the 2021 AAS Macauley Awards. The Macauley Award recognizes future space industry leaders by awarding and contributing to the professional development of a set of outstanding college and university students. 5 finalists and 1 winner were selected for each of the 2 tracks. And those 2 tracks are business and space policy and space and engineering. So business and policy is 1 track, science and engineering is the other track. Each finalist receives support to attend the Glenn Symposium, and each winner receives $2,000 cash towards the pursuit of their career in the aerospace industry. The finalists are tuned into the event, and we're happy to hear now from our science and engineering winner, Paula Pereira from the Massachusetts Institute of Technology. Paula, I'm looking forward to hearing your presentation. Please take forward.
Yeah, thank you so much for the introduction, Alan. So as Alan mentioned, hello, my name is Paula Vale Pereira. I'm currently in the last year of my PhD in aerospace engineering at MIT, and my PhD project is based on a collaboration with Stone Aerospace. So, waiting for the slides to come. Okay, so modern science has taught us that the 3 main ingredients for life as we know it is the presence of liquid water, an easily available energy source, and the presence of biologically essential elements. Ocean worlds such as Europa and Enceladus may fulfill all of those criteria. They have an under ice ocean, energy available from tidal heating, and might also have biologically essential elements inside their water. Ocean worlds might be our best bet on finding life outside the Earth. One big engineering challenge in that endeavor is to penetrate tens of kilometers of ice before reaching such oceans. Together with Stone Aerospace, I'm working on understanding how to perform that penetration task efficiently. My presentation today is entitled Experimental Results of Melt Probes in Cryogenic Ice for a Future Europa Lander. Next. The Arapan Ice Shell can be divided into 2 layers, a conductive, brittle outer section that ranges from about 100 Kelvin at the surface to about 250 Kelvin at the interface, and a convective, ductile inner section that is close to the melting point of water and easier to melt through. Together, those 2 layers are believed to have a thickness of about 20 kilometers. Next. There are 4 stages of penetration for the Arapan ice, which I'm here calling the starting problem, the cruise phase, the obstacle problem, and the ocean penetration. At the starting problem, there is little contact between the probe and the ice, so it's challenging to transfer much heat. The cruise phase can be divided into the brittle ice transit and the ductile ice transit, and they are characterized by a relatively steady velocity. We do not know precisely what the composition of the ice in Europa is. We know it's mostly salty water, but there might be blocks of concentrated salt, rocks, cracks, lakes, or even voids on the way of the probe. Passing through such obstacles is very challenging, so we call that interaction the obstacle problem. Lastly, the ocean penetration is the phase in which the probe reaches the ocean. Next. The stage that is expected to last the longest is the brittle ice transit. So if we develop a model that reliably predicts probe velocity in that stage, we will be able to estimate how much time it will take to reach the ocean. Next. There are 4 methods for ice penetration being currently studied: mechanical drilling, hot water drilling, thermal melting, and laser melting. Hot water drilling and laser melting, though, are still in the earlier stages of development, so the most common ones for steady-state ice penetration are mechanical drilling and thermal melting currently. While mechanical drilling can be made effective, it is significantly more complex than melting. The large and heavy required infrastructure also needs to be addressed before we can take mechanical drilling to Europa. Next. Melting, on the other hand, is not only the safest option, but also the one method that can be analytically modeled, making it possible to infer predictions and optimize time to ocean models. Next. Hence, our focus is on melt probes for the brittle steady state transit. This is important because it will help scientists estimate the amount of time it will take for the probe to reach the ocean and how much power it is needed for that speed to be achieved. So talking about models, next. There is a seminal model called the AMOT model, which was published back in 1967 and calculates the total heat necessary for a probe to melt and penetrate through the ice. The big takeaways from the model are that to optimize the probe efficiency, we need to maximize descent velocity, minimize the probe diameter, and tune the lateral heat, because insufficient lateral heat would cause the probe to get stuck, while excessive lateral heat would be simply a waste of power. Next. This analytical model, though, is full of simplifications and is not experimentally validated yet. So our goal is to tackle that validation gap, which will allow us to calculate the necessary power for a future lander and the number of years it will be needed to operate before it reaches the ocean. Next, we want to understand what happens on the back of the probe. Like, will the sublimated water vapor redeposit on the walls of the hole and close the hole again? We want to learn how to implement cabling on board the probe, especially if the hole does close back behind it, making it infeasible to store cables on the lander. We want to know how far off our experimental boundary conditions are from real case Europa. And we want to understand how far off the ideal analytical model is from the actual function of velocity with respect to power. And to do that, we use the Europa Tower. Next. Located at Stone Aerospace, the tower main component is a 3-meter-tall cryogenic vacuum chamber that hosts a column of ice of 2-meter height and 75-centimeter diameter. Very big. The ice is kept at about 100 Kelvin during tests, and the ambient pressure inside the chamber is kept below 10 millitorr. There are 2 thermocouple strings inside the ice, one at the center that we use to measure the probe's effect onto the ice, and one close to the walls that we use to validate the test boundary conditions. This is the closest to Europa currently available on Earth. As of now, we only have performed tests in pure water ice, but we plan on testing salty ice in the future. The difference in gravity between Earth and Europa is something we're still thinking about how to tackle, though. Next slide. The probes we are experimenting with are called the MVPs, or model validation probes. But I have to admit, they are also the most valuable players for my thesis. The probe was designed so that it would be possible to make direct comparisons between the experiments and the model. There are 4 components on the probe. Next. The first one is the power and thermocouple spool. So we can store the wire on the probe and have it to continue to descend even after the hole closes behind it. Next, a spool with an encoder that we use to measure the depth of penetration of the probe. Next, a cartridge heater. And lastly, the actual body of the probe. Next, we have performed 3 test campaigns so far. And we have used the first test campaign to learn about implementation challenges ahead of us, and the second and third test campaigns to actually gather the data we need for modeling. Next, the third test campaign was completed just a couple of weeks ago, so we are still analyzing the data. Here I will present an overview of the results from the second test campaign. Next. We tested 3 copies of the probe at 3 different power levels: 500 watts, 650 watts, and 800 watts. They all present similar trends and learnings, so let's focus on the MVP2 only. Next. Next again. So for MVP2, we had 800 watts input power level. We reached a depth of about 87 centimeters from the point where the back of the probe was flush with the ice surface and had an average velocity of about 44 centimeters an hour. On the plot, between the power on moment and the stalling moment, you can see the sequential peaks on the temperature measurements. Those are the thermocouples on the central string of the vacuum chamber. And that sequence of peaks shows that the temperature of each thermocouple peaked as the probe passed through it. The first peak is of a shallow thermocouple, and the last peak is of a thermocouple at approximately 90 centimeters deep into the ice. You can also see that the penetration depth, that yellow growing line, becomes very steady after an initial transient. This transient is the period between the start of the test and the hole closure. So next slide. We use 3 measurements to confirm that the hole behind the probe had indeed closed: pressure, temperature, and position. Could you run the video too? Oh, it's running. Thank you. After the orange vertical dashed line that you see there, the pressure monotonically decreases, meaning that there is no new dump of water vapor in the chamber. The probe rear temperature is steadily above 0. That thermocouple was located on the trailing edge of the probe at approximately 32 millimeters behind it. The probe descent rate becomes steady, meaning that we are at a relatively steady state condition. With those 3 pieces of information together, we can confirm the hole indeed closed behind the probe. The depth in which the hole closed is relatively shallow for all the probes, less than 1 probe length. This is important because when the hole closes behind the probe, the pressure starts to increase inside that pocket, raising above the triple point of water and allowing water to reach the liquid phase, which increases the heat transfer efficiency between the probe and the ice and decreases the necessary latent heat transfer. Hence, the closure of the hole increases the probe efficiency significantly. Next. With the results of the 3 different power levels, we were able to compare the trends of the experimental data with the Seminole model. The trends are very similar, but with a shift towards lower efficiency. We are currently working together with NASA JPL to refine the thermal models to close that gap. Next. On the first attempt to validate the model, we can notice 2 trends. Next. The first one is that at higher velocities, the probes are more efficient. This happens because at higher velocities, the heat that is lost through lateral dissipation is relatively smaller. Next, the second trend is that we are closer to AMOT predictions at higher speeds. This happens because at lower speeds, the idealities of AMOT model are too far from reality. But at higher speeds, the model becomes closer to the ideal condition. Next. I would like to conclude this presentation saying that our first set of experimental results confirmed that the hole indeed closes behind the probes, confirmed that the higher velocities happen at higher efficiencies, predicted the descent rates lower than the AMOT model as expected, presented well-behaved boundary conditions, and had successful measurements of penetration depth. Next. Our next steps are going to be to test our probes at different ice compositions, test probes with different instrumentations, and test probes that use hot water jetting to aid the descent. Next. Lastly, I would like to thank everyone that was involved in planning and running those very long test campaigns. Next. I would like to thank NASA for sponsoring this research, and I would like to thank everyone in here for awarding me the Molly Macauley Award and for listening to my presentation. Thank you.
Thank you, Paula. I actually read your paper and I was able to understand it. It was great. I have 30 seconds for an answer. Tell us any plans you have for field testing this under polar or Antarctic ice.
Yes, so there have been many tests in polar ice. The issue is that polar ice is relatively warm. It's about minus 20 Celsius. So the thermal effects are very different from the cryogenic one, but we can extrapolate some models from both behaviors if we have non-dimensional units. So that's for the future.
That's the 30-second answer. You won the prize. So
Thank
thank you
you.
very much. Thank you very much. All right, it's time for everybody to move forward to our next session, sustainable aviation. So click on your next session.